Hello everyone. Today I'm going to share our practice in deploying deep learning recommendation models at a production scale. This is a collaborative project between HKST and Alibaba Group. Personalized recommender systems are key infrastructure for many user-facing revenue-generating web services, particularly in e-commerce platforms. This system leverages deep learning recommendation models to provide accurate, personalized recommendations that improve customer experience and increase user engagement. Applications include web search, recommendation, and advertisement. And modern recommendation models utilize a large feature set that can be divided into dense and sparse categories. The dense continuous features such as user age and item price are processed by deep neural network layers. The sparse features such as a sequence of user or item IDs are transformed into continuous embedding representation via lookup operations in embedding tables. These two kinds of features are then fused and fed into densely connected networks, such as multi-layer perceptrons or transformers, to generate prediction like click-through rates or item scores. These embedding tables are typically large, ranging from 100 gigabytes to 1 terabytes. And the embedding lookup operations have low compute intensity, which are better executed on CPUs. In contrast, dense network components is better executed on GPUs. For example, a DLRM instance may require 48 CPUs and 1 GPU to accommodate both large embedding tables and dense layered computations. This figure illustrates CPU demands of Alibaba's DLRM service in the production cluster. GPU demands follow the same chain. Here, 3 stars indicate e-commerce promotion events, such as the Double 11 shopping festival. And we can observe a distinct diurnal pattern with a peak-to-valley executing 6 times. During seasonal promotion events, the peak load can be 1.3 times higher than regular peaks. Next, I will summarize 2 main challenges in resource provisioning when we try to deploy elastic DLRM service at such production scale. The first resource provisioning challenge occurs in daily DLRM serving. In shared cluster, frequently scaling DLRM provisioning based on changing load results in severe resource fragmentation. These figures illustrate the distribution of available CPUs and GPUs in a large GPU cluster, where both CPU and GPU allocation rates reach 90%. DLRM service owners experience prolonged scheduling times or even scheduling failures, although they have sufficient resource quotas. This severe fragmentation is primarily due to the high CPU to GPU ratio of DLRM inference instance. From their perspective, the cluster has over 30,000 fragmented CPUs and more than 200 fragmented GPUs. And the second resource provisioning challenge occurs during seasonal load spikes. Throughout the year, Alibaba hosts several large-scale shopping festivals when DLRM service experience significant load decreases. Provisioning from peak load at such scale results in significant underutilization, making it economically unviable. So, to handle these transient excessive load spikes, capacity loading is often necessary. In Alibaba, we maintain multiple purpose-specific infrastructures, some for training and the others for inference. When DLRM serving reaches peak hours, we wonder, can we temporarily load some GPU servers from training clusters, as training jobs are less latency sensitive and can tolerate interruptions? However, there is a mismatch between server configuration and DLRM resource demands. It restricts us to enable effective capacity loading. We next discuss about resource heterogeneity in modern GPU clusters. The left figure shows the distribution of CPU to GPU ratios across server nodes used for training and inference in Alibaba. Generally, nodes suitable for training tasks have multiple advanced GPU with high-speed interconnects like NVLink, but limited CPUs. It results in a low CPU to GPU ratio. In contrast, nodes optimized for inference tasks, especially DLRM serving, have much higher CPU to GPU ratios, typically a single GPU but many CPU cores. To accelerate CPU-intensive operations like data preprocessing and embedding lookups. We can observe that over 90% of DLRMs have CPU to GPU ratios greater than 20, whereas all multi-GPU training nodes have ratios below 20. Consequently, running DLRMs on training nodes quickly exhausts CPUs, leaving numerous GPUs stranded and unutilized by other tasks. So, as cluster operators, we aim to build a unified infrastructure that can integrate both training and inference workloads, optimizing resource multiplexing and minimizing fragmentation. In this work, we propose resource disaggregation for DLRM serving. This approach allows decoupled independent scaling of CPUs and GPUs. It also enables efficient resource sharing with other GPU-intensive AI workloads. GPU disaggregation can be achieved at different levels. We compare 3 possible approaches and justify our choice. At the graph level, a DLRM is represented as a compute graph with multiple operators running on CPU or GPU. We can partition this into CPU and GPU subgraphs, which can then be scheduled on selected nodes for disaggregated execution. At the API level, approaches like rCUDA intercept CUDA API calls and redirect them to remote GPU nodes for execution. At the hardware level, GPU disaggregation can be enabled with specialized hardware such as customized multi-hole PCIe switches and CXL technologies. We consider graph-level disaggregation viable for 3 key reasons. First, DLRM exhibits distinct resource consumption patterns. Second, it can easily support heterogeneous AI accelerators. Solutions at API level require considerable engineering for API compatibility and performance tuning. Supporting GPUs from different vendors will also require developing and maintaining distinct remoting layers for each platform. Third, it can adapt to the existing infrastructure. In contrast, all hardware solutions require specialized equipment. Also, we can utilize optimized RDMA network to provide scalability, stability, and SL guarantees for disaggregated inference. In this work, we introduced Qizhen, a large-scale DLRM system to enable GPU disaggregated serving through graph partitioning. In Qizhen, CPU nodes interconnect with heterogeneous GPU nodes via high-speed RDMA network. Qizhen automatically partitions recommendation models for distributed inference across CNs and HNs. It has served as the underlying infrastructure in Alibaba for core recommendation service for 2 years. Here is an example of how Qizhen works. It maintains 2 disaggregated resource pools that can scale independently. The GPU pool here covers both training nodes and inference nodes. The disaggregated instance of multiple services are placed on different nodes. When the user request comes in, it will be first routed to one of the front-end CN instances for embedding lookups and other CPU-intensive computations. Intermediate tensors are then transferred to remote Hadron instance on GPU nodes through RPC over RDMA network. After the Hadron instance returns result, the CN instance performs post-processing before sending the response to the user. Building this disaggregated serving system requires addressing several design requirements. First, transparency is essential. For production development, disaggregation must be transparent to model developers without requiring them to explicitly modify model architecture or implementation. Automated graph partitioning must support disaggregated inference for various recommendation models without affecting users or invalidating original optimization strategies. Second, we must maintain SL attainment. Since disaggregation inevitably introduces performance overhead, we need a joint optimization approach across various system components to minimize the impact on service performance. Third, the system must be scalable, which means that the performance must remain stable even with high traffic loads in production environments. This figure presents system components in Qizhen, and we highlight key designs in purple. In production DLRM system, the recommendation framework offers numerous optimization techniques to model developers. This optimizer typically applies sequentially, rewriting the original computation graph to generate an optimized version for deployment. Qizhen introduced graph partitioning and disaggregation optimization as final stage in the existing workflow. We employ a heuristic approach to split the GPU subgraph. We conduct offline profiling of different operators and characterize them as CPU-intensive operators or GPU-efficient operators. We perform a DFS coloring process to include the maximum feasible number of operators for GPU computation. In 80% of DLRM service, RDMA transfer size per request is under 10 megabytes. Our evaluation shows that the service performance can remain uncompromised at this size. We developed a unified operator called fieldgraph OP for RPCs. This operator aggregates tensors requiring transmission from the CN instance and send requests to one of the remote HN instances. To minimize memory copies between the computational framework and RPC system, we established a shared memory pool. Fieldgraph OP flags tensors for transmission and transfer control to the RPC system. We leverage GPU direct RDMA for zero-copy data transmission. The resource manager is responsible for placing a group of CN and HN instances into a shared cluster. Different types of instances can be scheduled and scaled independently. A service remains available if at least one CN instance and one HN instance are working. To ensure recommendation service SLOs, the resource manager follows topology of well-scheduling and allocation principles. First, all instances are confined within the same pod, as cross-pod RDMA connection can cause over 50% performance degradation. Second, collocating CN and HN instance within the same S switch offers superior performance. So we prioritize this affinity and aim to pack instance under the same S switch. Also, to prevent bursty resource consumption on single node, the resource scheduler can limit node-level deployment density based on service configuration. During peak seasonal traffic, the scheduler incorporates more instance density constraint as a NIC switch layer to prevent network saturation. This figure illustrates the intro-node topology of a typical multi-GPU HN and the typical CN. In the node-level allocation, the resource manager separately considers the HN instance and CN instance. For HN instance, the interconnect between GPUs and RNICs significantly impacts performance. The manager prioritizes assigning RNIC and GPU on the same PCIe switch for each HN instance. And for CN instance, since CPU nodes typically have only one RNIC, so the manager prioritizes allocating CPUs under the same PCIe switch connecting to the RNIC. The third key component is the communication scheduler. In Qizhen, we extend the native raw stack and implement a middleware to leverage RDMA in a virtualized environment. The in-cache flow will happen when many CN instances simultaneously transmit data to a limited number of HNs. This table shows how a high-value in-cache traffic degrades overall performance, including long-tail latency and reduced throughput. The in-cache window size and processing order of delayed requests critically affects in-cache control effectiveness. Qizhen adapts in-cache window size according to network and PCIe link congestion level. The HN instance periodically connects sends CMP counts and calculates congestion levels. Qizhen also reorders requests in the cache queue to maximize SLO attainment. It calculates deadlines by subtracting transmission overhead from the sum of current time SLO. Now we show how Qizhen performs. This table outlines high-level characteristics of 5 production models. The machine specification is as follows. I will quickly go over Qizhen performance of various models on the different RPS levels. More results can be found in the paper. Even in the worst case, such as model XL, who has the largest communication volume, Qizhen only suffers at most 6% performance loss. We show that Qizhen can maintain service performance under high traffic in real-world deployments. Next, we compare resource requirements changes for DLRM's instance before and after Qizhen deployment. Qizhen reduced the strict resource requirements of inference services. Actual instance requiring GPU allocation need fewer than 12 CPU cores and less than 24 gigabytes memory. In contrast, CN instances which are CPU intensive and no large embedding tables require over 48 CPU cores and more than 240 gigabytes memory. It shows that Qizhen can separate resource requirements of DLRM inference services. By separating resource requirements, CN instance can run on nodes where GPUs are exhausted but CPU remain available, while HN instance can run on nodes with insufficient CPUs but available GPUs. The analysis shows Qizhen can significantly reduce cluster CPU fragments by 53% and GPU fragments by 27%. So it can utilize fragmented resource to meet deployment requirements. During e-commerce promotional periods, we leverage Qizhen to borrow training nodes to scale out DLRM inference services, meeting short-term yet high-throughput traffic peaks. It demonstrates the ability to handle production-level traffic loads. It enables the recommendation models to efficiently utilize training nodes without straining any GPUs. Finally, we engage in some discussion and possible future explorations. First, is disaggregated serving necessary for all workloads? By knowledge, PD disaggregation in LLM inference attempts to decouple the GPU-intensive prefilling phase and IO-intensive decoding phase to different machines. Our work on DLRM disaggregation attempts to decouple CPU computation and GPU computation. Philosophically, all these disaggregated deployment approaches try to transform workloads from a resource provisioning perspective, so that diverse resource requirements within the same workload can be decoupled to adapt to the infrastructure in data center. In other words, all workloads with heterogeneous requirements during inference can attempt disaggregation approaches for efficient deployment. Disaggregation deployment also brings considerations for tolerance. Disaggregation introduced the network as a new resource dimension, but this resource is not unlimited. So we need better performance isolation to guarantee service performance at the levels of both node and NIC switch. Deploying inference instance on training nodes also bring higher deployment density. So we need more fine-grained management to reduce the impact on service during single-point failures. Here are 3 key takeaways of today's presentation. We have also released a production DLRM serving trace as part of the Alibaba cluster trace program for future research. I'm happy to take any question.